Computers are fast, like really fast. They feel like literal magic, and yet they didn't get to this point out of nowhere. Computers have been improving for the past 80 years, but it turns out most programmers' mental models about how they work are stuck in the 70s. The actual workings of a CPU nowadays is very different from how it worked back then, and unfortunately, it's very common to go without learning much of it. So, in this video, we'll start with a CPU microarchitecture that is fairly simple and try to make it faster, hopefully rediscovering most of the techniques hardware designers used to get us to where we are right now. The obvious place to start is to define the initial model of the CPU that we will improve. So, let's start with this. Two internal buses, data and control, a clock that synchronizes all operations, then a place to store the address of the next instruction called the program counter, and another to store the current instruction called the instruction register. The instruction register directly feeds into the control block, which generates appropriate control signals based on the current instruction. Control signals are basically certain flags sent to these functional blocks that control how the data will flow. For example, a PC in control signal allows data from the data bus to flow into the PC register. Apart from that, we'll need access to actual memory, which is done through the memory data register, MDR, and the memory address register, MAR. These communicate via external buses with main RAM. Next, we have the ALU with a few temporary registers, and finally, our general purpose register file. Let's try to run a sample instruction with this architecture. Well, we have to first load the instruction from memory, for which we have to move the data from the PC register to the memory address register. The control signals here are PC out, MAR in, and mem read. After this, we will wait for RAM to actually give us the instruction at that location. In the meantime, we can actually increment the PC register to make it point to the next instruction. Once we have our instruction in the memory data register, we enable MDR out and IR in, finally actually getting our instruction that is to be executed. Based on this instruction, the next control signals will change, decided by a decoder circuit in the control block. In this case, it will be R1 out, Y in, then R2 out, ALU add, Z in, and finally Z out, R1 in. After this, the next instruction will be fetched and the cycle continues. Pretty simple, right? Do note, the specifics of control signals here are for a hypothetical processor, but you can expect them to look similar in really old processors. So, how do we make this system faster? Well, we have a couple of low-hanging fruit that we can quickly try. Our first point of interest is the clock. Since it synchronizes all CPU working, obviously, a faster clock means the operations of the CPU happen faster. Seems like an easy slam dunk for us here, right? But there's two major problems with this. The first one is heat. Higher clock speeds means more power draw, which means more loss in the form of radiated heat. We get around this using heat sinks and other cooling mechanisms, but they don't reduce the heating effect of the CPU itself to zero. The other issue is the actual physical constraints of digital signals. Computers are built from logic gates, which have an inherent delay to them. Also, simple wires themselves need time to transition from logic 0 to logic 1 or vice versa. We have a practical barrier to increasing clock speed beyond a certain point. So, what else can we do? Another easy pick is to increase the number of general purpose registers that we have. This can help in the implementation of certain algorithms. For example, if I have an algorithm which uses 6 variables, but only 4 general purpose registers are available, 2 of the variables would have to go into the stack, which in this case would be in RAM. However, there is an issue with this as well. Most CPUs are designed on the basis of what is called an ISA, that is, an instruction set architecture. Simply put, it is a definition of a lot of things: what data types the CPU natively supports, what memory model the CPU works with, and so on. It also defines what instructions the CPU supports, as well as how the instruction is encoded in binary. Whenever an ISA is updated, designers make sure that older programs depending on the ISA do not break, so the binary encodings that exist for certain instructions stay the same. For example, take the x86 instruction, increment AX. It encodes the following binary. x86 has 8 general purpose registers, which means 3 bits can select a specific one. In this case, the last 3 bits fulfill this role. As you can guess, adding just one more register would mean adding an extra bit to actually allow selecting one of these correctly. This isn't impossible, just annoying. For the Intel example, additional registers R8 to R15 were only added by the x64 ISA extension, which is very recent in the grand scheme of things. Another thing to try is to extend the ISA itself with new instructions that do more work individually. Assuming Turing completeness of our CPU, of course, you could implement algorithms in software that does the same thing. But more instructions in the algorithm means more time required to fetch them in total. If the algorithm is very regularly used, then converting it to a single instruction makes complete sense in terms of performance. In older CPUs, even instructions like multiplication and division weren't implemented because of hardware complexity. So to enable adding of complicated instructions without having to resort to adding actual hardware for them, the concept of micro-operations was invented. To understand these, we have to first understand how the control block used to work. As I said before, the control block generates appropriate control signals for an instruction. The control block used to look like so. Part of the circuit breaks down current processor state into separate signals, then raw combinatorial logic drives individual signals. For example, on the first cycle of the execute stage, R1 out is enabled if the instruction is a move or add or sub or so on, and the source operand bits are 0, 1. Encoding logic like this in literal logic gates is very tedious. For simple instructions like a move, it's not too bad, but if we wanted to add signals for more complicated instructions without adding the hardware for them, generating 8 to 9 cycles of control signals is very tedious. With micro-ops, the idea is any instruction can be further broken up into elementary operations that the CPU can execute super easily in a single clock cycle. For the simple register-to-register moves, there'd probably be only one micro-op. For complicated instructions like multiplication or division, however, you would have a sequence of micro-ops, which together are called a microprogram. All these microprograms are stored in a microcode ROM. Whenever the CPU wants to decode an instruction, it converts the instruction to a starting address in the microcode ROM and executes the microprogram, which just means running the elementary micro-ops in sequence. Implementing complex instructions just means adding a mapping from the instruction to the starting address in the microcode ROM, and then writing the micro-ops for that instruction in that place. It's easy, extensible, and super convenient. As computers evolved, we saw more and more algorithms implemented as microcoded instructions like PCL, MUL, QDQ, as well as more and more microcoded instructions implemented in hardware like multiplication and division. That brings us to the end of basic updates. These definitely increase the speed of the CPU without too much effort, but to get real speedups, we have to rethink the architecture itself. Which brings us to pipelining. Taking a look back at our diagram and how we actually ran an instruction, you can fairly clearly split the process into 2 steps. The part of the instruction cycle that fetches the next instruction from memory, and the part of the cycle which actually executes the instruction. The hardware for the 2 parts is clearly split through the use of buffer registers and the IR. So what's stopping us from running both at the same time? Well, the problem is obviously that we need the output of the fetch stage before we can execute the instruction. But when the instruction is executing, as long as it's not going to access memory, we can actually already start fetching the next instruction. This parallel running of multiple instructions in different parts of the processor is called pipelining. So let's implement this. I'll just rearrange some of the things in the diagram and make the control signals implicit so they don't clutter everything up. Here's where the separation between the stages comes in. Something we have to do to achieve this is to add a buffer in between the stages. In this case, it stores the next prefetched instruction, which will be loaded into the IR when the previous finishes. With pipelining, as long as individual stages take less time than the full time required to process an instruction without pipelining, the total throughput of instructions running through the CPU will increase. We can visualize the effects of pipelining with a simple diagram. So let's take a sample program for that. For the diagram, on the left we have the instruction names, and at the top we can write the current time step. Now we can fill in what instruction is in which stage in the blocks in the center. Without pipelining, the second instruction can't start before the first completely finishes. So we'll find that I2 starts at T3, I3 starts at T5, and so on, giving us something like this. We'll assume for simplicity that the fetch stage takes 2 clock cycles and the execute stage takes 5 clock cycles. With this non-pipelined version, every instruction takes 2 plus 5 is 7 clock cycles to execute. So for the 7 instructions we have, it takes 7 into 7, which is 49 clock cycles. With our two-stage pipelining, however, we can begin fetching the next instruction while the previous finishes, giving us a good general speed up. Here, the first thing to note is that for the CPU to execute synchronously, all the stages need to take the same amount of time. In this case, we can pick the 5 cycles for one stage to complete, which is the max of the times taken for every stage. With that, here's how we compute the time taken for 7 instructions to execute with our two-stage pipeline. The first instruction takes 10 cycles, since it can't get the benefit of simultaneously executing with anything before it. However, any new instruction will be finished every single time step after that, which is 7 minus 1 is 6 instructions for a total of 30 clock cycles. So the final time taken for 7 instructions is 40 cycles. Notice how that even though the time taken for one instruction to complete went from 7 cycles to 10 cycles, the total time taken for 7 instructions altogether went down. We can go further, of course, by splitting the execute stage too, in this case into decode and execute. The decode stage generates control signals and reads operands based on the instruction, and the execute stage actually does the computation. As before, with any split like this, we need to introduce a buffer between the stages, in this case storing the control signals or microops and the operand values. Let's calculate the speed again. I'll assume it takes 1 cycle to decode and 4 cycles to execute. Here, the total number of clock cycles required to execute one instruction stayed the same. It's still 7, but the time per stage can go down from 5 cycles to 4 cycles since the maximum is lower, giving us a total of 9 times 4, which is 36 cycles. It is again faster. And we don't have to stop here. Keep splitting the biggest stages into smaller ones and we achieve hyper-pipelining. Recent processors have even gone up to 22 stages, but for this video we'll assume that we have 5 major ones. Fetch and decode are pretty much the same. Execute, where we run an operation and compute a memory address. Memory access, where we read or write memory. And write back, where we write the output of the instruction to a register. Generally, more pipeline stages are just smaller splits of these major 5 ones. Well, this all seems pretty nice, right? A great speed up by just splitting the instruction execution into steps. Well, pipelining like this causes some pretty major problems. Let's have a look at our instructions again. This is obviously some pretty weird code. Rewriting R3 with different operations based on R1 and R2. More commonly, we'd have something like this. By simply changing operands for the instructions, we already encounter our first problem. Remember, a register's value is read in the decode stage of the pipeline, and a register is written back to in the write back stage. So, in this case, focus on I2 and I3. I2 writes R1 plus R2 to R3. It will read R1 and R2 at the decode stage, which is time step T3, compute R1 plus R2 in the execute stage T4, then do nothing in the memory access stage T5, and finally, at the time step T6, actually write this result into the register file. However, instruction I3 at this point is way past its decode phase already, which happened at T4. At that point of time, it wanted the register value R3, but we didn't actually have the updated value of R3, so it picked the wrong older value. What this means is that the program just won't work as expected. To use some CS terms here, the instruction I3 is dependent on I2. This dependency is a read after write dependency, or RAW, because the value of R3 is read after it's just been written to. This type of dependency constitutes what is known as a data hazard for the pipeline. There are other types of dependencies as well, namely write after write, that is a WOW dependency, and a write after read, that is a WAR dependency. But these other two aren't actually hazardous to our pipeline yet. Back to our example, you can see that I4 and I5 are also raw dependent on I2. With I4, we get the same problem. I4 decode is supposed to happen before I2 write back. I5 is different, however. Its decode happens at the same time as I2 write back, which means that it doesn't really have to worry about anything. So, now the question is how we actually get around this problem. Well, one option is just waiting. The decode stage figures out what registers are being worked with. It can keep track of what register an instruction is writing to in some sort of memory. Then, if the next instruction is reading from that same register, the decode will not write to its buffer. This is called a pipeline stall. Of course, this scales with the number of pipeline stages. The decode logic will have to keep track of 2 registers in our case, but this isn't optimal. The problem is that we are basically giving up on pipelining here. Most of the time, instructions that are nearby are dependent on each other because that's just how we humans think. And if we have to stall the pipeline every time a hazard like this comes up, we'd be losing a lot of throughput, so we need a different plan. The core of our problem is that we don't actually have the latest value of R3 in the register file before decoding I3. But if you notice, we actually have computed the value of R3. It's just being output to the buffer of the execute stage. So, what we simply have to do is add a little connection, moving data from there to the decode stage. Then we can select between the data from the register file or the data incoming from the execute stage. And this selection is based on the same logic that I described for stalling the pipeline. For I4 to work, we'll have another connection from the buffer of the memory access stage back the same way. This solution is called operand forwarding. We are forwarding results of instructions to the next instructions a bit early. So that's one problem down. What's next? Well, let's introduce some control flow in our example instructions. Here, we want to jump execution to I2 if R3 and R1 are equal. I'm guessing you can see the problem with this one pretty easily. The pipeline's fetch stage relies on knowing what instruction to fetch next. Usually, it's just the next instruction, so the fetch stage can just increment the program counter by the size of the instruction. With conditional jumps, everything breaks. The fetch stage will fetch I6 and I7 before the execute stage realizes that the jump needs to be taken. If the fetch starts fetching the right instructions after that, I6 and I7 will wrongly be executed. So something called a pipeline flush has to happen. Instead of going on with the bad instructions that are in the pipeline, the data in the fetch and decode stages is discarded, and the pipeline starts over with fetching I2. Obviously, this is bad because we are doing additional work on instructions that aren't supposed to be executed, which means wasted power. This is called a control hazard for the pipeline. One thing we can do to alleviate this is to introduce a stall again. The fetch stage can quickly check if the instruction is a jump, and if it is, stop fetching further instructions until it receives confirmation from the execute stage. This means less wasted power, but is still bad for performance overall, as we saw before. This is where branch prediction comes in. The idea is simple. If the fetch stage needs to know the next instruction, it can just try to guess. The guess doesn't have to be perfect. If things go wrong, we can still do a pipeline flush. But by guessing, we would ideally be reducing the number of times we have to flush. In the fetch stage, if we fetch a conditional jump instruction, we need a small circuit that will try to predict whether the current branch is taken or not taken. Branch prediction algorithms are algorithms that do just that. Originally, I wanted to get into these algorithms in this video, but as I'm writing the script, I can already see that the length is getting pretty ridiculous. So keep an eye out for a separate video on that. So with branch prediction, that's 2 problems down. What's next? Let's bring back the code and make one tiny tweak to see the problem. Do you see it? Looking at our current computer, we have this block for accessing data from RAM. Remember, all instructions and data live in RAM. The problem here is that we can only really access one thing at a time. Either the next instruction, which is something the fetch stage is doing every single time step, or reads and writes to some data that the memory access stage might want to do. Because this is the case, anytime we see the memory access stage working alongside the fetch stage, we have a problem. In this case, T4 is immediately an issue. Fetching I4 coincides with memory access for I1. So, how do we get around this? Well, stalling is an option, but as usual, it's a last resort. A much better idea is the use of caches. We can have a separate cache for instructions, which the fetch stage is constantly working with, and we can have a separate cache for data. Since these 2 caches are different units of memory, both of them can work at the same time. Only occasionally will the caches be updated from RAM or writing back to RAM. Usually, of course, there's several levels of caches which exist between RAM and the MMU, but I won't go into too much detail about that, in this video at least. The idea of caches is useful not just to decouple instructions and data, but also to speed up certain parts of the CPU. For example, the instruction decoder circuit can have a cache for decoded micro-ops corresponding to certain instructions, so that it doesn't have to do it every single time the instruction comes in. There's also several caches in the branch prediction part of the circuit. I'll probably cover those in the branch prediction video. But with that, we have finally reached the conclusion of pipelining. With additions of operand forwarding, pipeline stalls and flushing, branch prediction and caches, we get an actual fully working implementation of a pipeline. Pipelining shows us that we don't have to wait for one instruction to finish before starting the next. We are going faster, but still finishing instructions one at a time. But what if we could go one step further? What if we could do multiple things at once? I don't mean this in the way of multi-threading, where different parts of the program can be handled by different cores in the CPU, but within a single instruction stream. That line of thinking leads us naturally to the idea of parallelism. The easiest thing we can do to allow for parallelism like this is just make the programmer do it. There's plenty of places in programming where there are operations you want to do on a whole set of data. So you'd loop over that data, running said operation one element at a time. Here's an example of that with a simple n-dimensional vector addition function. This function compiles to some assembly. In this case, I'm just showing the part that actually does the computation. If I had n elements in the initial vectors, these 3 instructions would run exactly n times for each element. One form of parallelism is supporting running an operation over a whole set of data with a single instruction at once. This is SIMD, single instruction multiple data. The idea is we have a new set of registers, some power of 2 times wider than our general purpose registers, and dedicated instructions to work with these registers. The SIMD instructions interpret the wider registers as a set of individual elements and perform their operations on them independently. To add this to our microarchitecture, we have to extend our register file and add a vector execution unit and allow for wider data access in the memory access stage. With SIMD, the above instructions that I showed changed to these 3 vector instructions instead. In this case, it's using the XMM registers, which are 128 bits wide. So 4 elements are executed at once reducing the total number of times these instructions have to run from n to n by 4. This is obviously big. What we have just done is parallelism in terms of data, still executing one instruction per cycle, but doing more per instruction than before. However, if we ever want to go faster than this, we have to somehow go beyond the limit of one instruction per cycle. If we ask the question of why does this limit exist in the first place, we get two major reasons. One, we have a single execution unit. If we had 10 add instructions in a row, they would certainly have to go one at a time because the ALU can only run one operation at a time. And two, programs are sets of instructions to be executed sequentially. Wait a second. The first part can be overcome by some additional circuitry, but is that second part even true? Let's take an example program. Take a look at the first two instructions. Despite us writing them in this specific order, we could execute any one of them first, or even at the same time, since there are no dependencies between them. Turns out you can find such independent sets of instructions in basically every modern program. Exploiting this is the idea behind something called instruction-level parallelism and is the basis of all modern computers. So let's take a look at how we could achieve this in our processor. Let's try executing two instructions at one time at least. One thing we can do to do this is just duplicate everything. Well, not everything, but a lot of our pipeline. The fetch stage can pull in a bigger buffer of instruction memory, and the decode stage can try to decode two instructions at the same time. The decode also has to check for dependencies between the instructions, and beyond that we can introduce the split. The decode stage can now forward the decoded controls or microps between the two different paths as long as no dependencies are found. Now, I'm not going to show the entire data path here because we do have a pretty major issue with this idea. With this system, going wider with more than two instructions means you need to duplicate a lot of logic that is hidden in this diagram. It gets unfeasible pretty fast. And the more important point is that we don't want the programmer to worry about the details. With the way we are doing it right now, executing two instructions only works if the programmer writes two independent instructions one after another. Thinking about it logically, most programmers tend to not think in terms of the CPU, but in terms of chains of operations. Due to this, it's way more common for instructions that are dependent to be right next to each other. What this means is reaching an ideal throughput of 2 instructions per cycle here is fairly uncommon. What we actually need to do is to try to catch these independent instructions with a wider net and execute them using some smarter system. To do this, we'll make the fetch stage get a bigger buffer of bytes and make the decode way more instructions at once. It can then output the decoded microps to a microp queue, and we'll try to execute as many of these as possible. Let's get a clean slate here for now and figure out how to do this. Let's bring back the parts of the system that are relevant: the register file, data cache, microp queue, also the ALU. But the idea is we want more execution units, so we'll have to duplicate it a bunch for sure. Generally, instead of duplicating the full ALU, we'd have different functional units capable of doing different things. Every functional unit has a certain clock cycle count that it will require to finish its processing. For example, the second block can finish in a single cycle, but division may take up to 50 or 60 cycles. Here's the fun part now. We have to invent an algorithm that runs through our microp queue and issues the microps out to these functional units, keeping in mind the program should behave correctly, as in any changes to the order we make shouldn't change the final output of the program. The simplest thing we can do is just iteration. Go through the microps and check whether a functional unit is available for it. If there is, and the operands required for the microp are available, we can go ahead and issue the microp to that unit. As we go on doing this, at some point, we'll hit a microp that can't be issued, either because some other microp is already allocated to the functional unit, or because the relevant operand registers are not ready yet with the latest value. This is where, for now, we'll just have to wait for the necessary conditions and then issue the micro-op when ready. To implement this in our architecture, we'll need a bit of bookkeeping and control. We'll record the statuses of the micro-ops and the statuses of the functional units that can be free or occupied. We'll also record which functional unit is currently producing the value for each register. From this, figuring out whether to issue a micro-op is a simple combinational logic circuit. For a micro-op, we can check the register statuses to confirm whether the relevant registers are free, and also check the functional unit statuses to confirm whether there is a free space to go. If these conditions succeed, we can issue the micro-op to the functional unit, that is, just send it through. Let's run through an example to see how this will work, imagining that all of these instructions are individual single micro-ops for our hypothetical processor. We have to start by initializing all the statuses. We look at the first micro-op. R0 is not yet written to by anybody else, and the load unit is available. So we can go ahead and issue this one. We'll mark R0 as the destination of functional unit 5 and the load unit as busy. Next cycle, we try to issue the add instruction. No problem here. R3 and R4 are both ready and the integer adder is free. So this one goes through to unit 1. We can update R2 status accordingly. Now comes the subtraction. In this case, R2 isn't ready yet according to the register status. So this one can't be issued yet. We have to stall for at least one cycle. Once the adder finishes the R2 computation and writes it back, R2 becomes available, which in turn allows our stalled instruction to be issued. Next up is the IML. No dependencies here, we can issue and move on. Next cycle, we get the add instruction again. This one waits on R1 because of the IML. Finally, we have the move, which waits for R3. Once that's issued, depending instructions are free to complete at any time. That's it. We successfully parallelized execution at an instruction level. What we have done here is allowed for multiple micro-ops to be running at the same time. Very similar to our duplicated pipeline idea, but with much less hardware. We are issuing operations in order to preserve execution correctness, but we are allowing instructions to finish at whatever arbitrary time. However, we are still not running optimally. Take a look where our algorithm stalls. It is exactly where there are dependencies between different instructions, because the relevant registers are then marked as currently busy and our issue condition fails. If we want our scheduling to be faster, we need to remove these stalls. Let's revisit why these dependencies matter in the first place. Write after write dependencies cause stalls because we have a specific order in which registers should contain values. For example, for these instructions, we want R1 to contain the result of the add after execution. If we were naive and didn't stall for the add, we'd issue IML and add very fast, but the IML would take longer to finish and hence would output its result later than the add. Write after read dependencies are pretty similar. In this case, we have to be sure that the write of R3 happens after R3 gets read for the add micro-op. Aside from these two, we also have raw dependencies again. Raw dependencies between micro-ops just means that the operand of a future instruction is currently being computed. We can't really change the fact that the functional unit has to wait for its operands to work, but we can do one interesting thing. Instead of waiting for the operands to be ready before issuing, we can go ahead and issue anyways, just not directly into the functional unit. Instead, we'll place them into a small holding area near each functional unit called a reservation station. There are multiple reservation stations per functional unit, and they can hold the micro-op along with tags indicating where its required operands will come from. We can connect the outputs of all the functional units to a common data bus, which can loop back into the reservation stations. Once a functional unit completes a micro-op, it will output the data along with the tag. All reservation stations can then match this tag from the data bus. And if it matches, it means that the operand has just been computed and we can use the value. No need to wait for the register file to update at all. The question now is what exactly these tags can be. We could just use the register names, as in this add R1, R3, R5 would have the reservation station which keeps track of tags 3 and 5, and after the add, it will output the answer with the tag 1. But this idea has a problem which isn't super obvious related to var and wav dependencies. Here's an example. In this case, the add and idiv get issued and a sub gets placed in a reservation station, as it depends on the value of R1. We'd expect the sub to use the output of the idiv instruction, but the first add will finish first and broadcast the output using tag 1. When this happens, the sub will match that and use the wrong value. Clearly, there's a difference between the values of R1 at different points of time, so the tag has to reflect that. One simple solution to this problem is to use an ID of the reservation station as the tag instead. For our example, when we come across the first add microp, we'll issue it to a reservation station and keep track of a mapping where R1 is associated with the ID of the reservation station. Next, when we issue imul, we'll change this mapping to the ID of the new reservation station instead. Now when the sub is issued, we'll automatically assign the latest tag. This process is called register renaming for hopefully obvious reasons. We use registers defined by ISA R0 through R7 when writing programs, but the processor renames those references to something completely different for internal use. By doing this, we are able to get around the problem of var and wav dependencies. However, even this system has two major flaws. Precisely stopping program execution because of any processor exception or interrupt becomes impossible. Imagine our idiv in the previous example accidentally divided by 0, but further instructions like sub had already finished executing. It is impossible to know in that case where an exception occurred. An arguably bigger concern, however, is how any of this even works with branch prediction at all. Take this as an example. If at any point the jump if equals instruction gets mispredicted, the wrong instructions may end up in the instruction stream and in the microp queue. If any of them get issued and finish execution before the branch prediction has been verified, with the current method there's just no way to roll back any of it. Fortunately for us, this is solved by a very simple upgrade to our system, and that is to replace our microp queue with something called a reorder buffer, or ROB for short. Like the microp buffer, microps are pushed into the ROB, but they don't get removed as soon as they are issued. No, instead, they wait until the microp finishes executing. When a functional unit wants to write back a value to a register, instead of immediately writing it to the register file, the output goes back to the ROB and is marked as complete in there. Every clock cycle, the ROB checks the front microps or multiple microps, and if they are complete, allows the write to the registers to go through and removes them from the buffer. This final check where microops are removed and changes are applied is called microop retirement. Notice what happened here. When we introduced ILP, we had a fully in-order process for issuing microops and an out-of-order process for execution and completion of said microops. And the out-of-order completion was what was causing the issues. By introducing the ROB, we still have in-order issuing and out-of-order execution, but we are able to return back to in-order retirement. Now, if any issues occur when executing any instruction like an exception, the functional unit can output this exception to the ROB, and the ROB will stop execution precisely and not apply any further completed instructions. Similarly, if the branch prediction logic mispredicts some branch, the ROB would be able to cancel any effects of further completed instructions. And that's just great. You may have noticed that I barely talked about memory references in this whole parallelism section. If we just have the load store unit connected to the data cache, like in the current diagram, then loads and stores being cancelable in the way that other instructions are won't work. So instead, the load store functional unit connects to load store queues. These queues act like the ROB but for loads and stores. They will only process the loads and stores when the instruction is retired from the ROB. I promise we are almost done, but there is one final tweak we'll do. Using reservation station IDs as tags works fine, but it's very hard to scale. And it muddies the responsibility of a reservation station as not just places to hold micro-ops, but also places to store intermediate values. So modern processors do something different. The actual place where values are stored is shifted to a different buffer, something called a physical register file. The physical register file is much larger than the register file that has persisted throughout our upgrades, so we can store many more values this way. Register renaming is done as a step just after the decode stage, so just before the micro-ops enter the reorder buffer. In this case, the references to logical registers are replaced by indexes into the physical register file. The reservation stations are then simplified to schedulers, and the tags that are used are just these simple indices into the physical register file. And that's about as far as we'll go today. What we have derived is very close to modern computer architecture, and I hope I was able to make it intuitive enough. I wanted to go through and run an example program on the final machine, but I have written about 4 different versions on how to do that, and all of them sucked because there's just way too much to keep track of. Of course, I haven't covered everything. Clock and bus timings, DMA, branch prediction algorithms, cache mapping, decoders, micro fusion, and so on are topics that I want to make videos on soon. So I do hope you stick around for those. I've added the links to many of the resources I used as research in the description, so if you want more details, you can always refer to those. I would specifically like to point out Agner Fogg's microarchitecture breakdown and optimization guide, which has been an absolutely amazing reference. With all that being said, that's all for today. Thanks for watching and see you next time.